From time-traveling pool balls to information-eating black holes, the mysteries of our universe are as confounding as they are captivating. One of the mysteries, called the Fermi Paradox, has haunted us for years. But something terrifying has come up, and scientists hope they are wrong about this solution to the Fermi Paradox. Why is that? Well, let's see what the experts have to say. As a species, humans have accomplished much to be proud of. We have adapted our environment to meet our needs, and we are even contemplating colonizing other planets once we outgrow this one. Despite our highly developed understanding of reality, there are several paradoxes that suggest reality may not work quite as we think it does. There are many perplexing mysteries in the world, such as time-traveling pool balls and information-eating black holes. What are these paradoxes, and is there any hope of resolving them? What is it? And why are scientists hoping they are wrong about the solution to the Fermi Paradox? The Fermi Paradox poses a question that has puzzled astrobiologists and other scientists for decades. Where are the aliens? Enrico Fermi, a Nobel Prize-winning scientist, coined the term during a casual luncheon chat in 1950. And ever since then, the question has continued to baffle experts. The paradox rests on the idea that, given the universe's vast age and size, aliens should have visited Earth by now. Our solar system, in comparison to the universe, is relatively young, at 4.5 billion years old, while the universe is estimated to be 13.8 billion years old. With enough time, interstellar travel should be possible, so why haven't aliens come to Earth? The observable universe spans approximately 92 billion light-years across and is growing at an accelerating pace, according to data acquired by telescopes. This means that aliens, who have had billions of years to develop and disperse throughout the universe, would have to travel across immense distances to reach us. When Fermi first posed the question, scientists only knew about planets in our solar system. However, in 1992, astronomers discovered planets revolving around a pulsar, and a few years later, the first exoplanet orbiting a sun-like star was found. Today, there are over 4,500 verified exoplanets, with new ones being discovered every year. The sheer quantity of extraterrestrial worlds raises the possibility that there may be a lot of life in the cosmos. There are countless potential explanations for the Fermi Paradox, with both experts and laypeople proposing hundreds of theories over time. For instance, in 2015, researchers who analyzed data from the Hubble and Kepler satellite telescopes concluded that Earth was probably a relatively early bloomer. They found that only 8% of the potentially habitable worlds that will ever exist in the universe existed at the time of Earth's formation, roughly 4.5 billion years ago. This finding provides one possible solution to the Fermi Paradox. The arrival of aliens may happen eventually, but it's not something we can expect in the immediate future. It's also possible that the existence of life in the universe is precarious and doesn't last for extended periods. A 2016 study suggested that rocky planets experience a favorable window for the emergence of life, typically around 500 million years after their formation, when liquid water becomes available. The scarcity of life forms in the cosmos could be due to the challenge of maintaining habitable conditions during the early billion years, rather than the difficulty of initiating life itself. Moreover, the bottleneck preventing the development of advanced civilizations might occur much later in their evolution. Many intellectuals have put forth the hypothesis that civilizations tend to vanish soon after reaching a certain level of technological advancement. Earth provides some evidence supporting this claim. For instance, during the Cuban Missile Crisis in 1962, humanity came dangerously close to a nuclear war. Additionally, anthropogenic climate change poses a significant threat to the planet's biodiversity, suggesting that we might be on the brink of wiping out much of the remaining life on Earth. These factors, among others, complicate the search for extraterrestrial life. Furthermore, it's worth considering that many extraterrestrial civilizations might not even be aware of the existence of other worlds to explore. Alien psychology could play a role in their lack of interest in contacting or visiting Earth. While there may be numerous advanced alien civilizations out there, the majority of them might simply not find Earth and its inhabitants intriguing enough to engage with. In this scenario, humanity would have to prove itself intelligent and deserving enough to be included in the galactic community. Alternatively, The majority of sentient aliens might actively avoid contact with their cosmic neighbors out of fear that such interactions could lead to their own subjugation or annihilation. This line of thinking, endorsed by many academics including the late Stephen Hawking, serves as a justification for why humanity should not aggressively promote its existence. On number 2, we have black hole paradox. The universe has a deep appreciation for information and values its preservation, disliking both the creation of new information and the destruction of existing information. Information simply exists across the cosmos without any inherent ability to create or destroy itself. To understand why information needs to be kept, we must first define what it is and its significance in physics. Determinism governs physics, which allows us to predict the future behavior of a system using physical principles. Our understanding of physics enables us to make accurate predictions that carry our knowledge from the present into the future, giving us insight into the behavior of everything from a single particle to the entire cosmos. If we have complete knowledge of a system, we can use the same physical rules to explore the past as well. Information is maintained due to this reversibility, and the basic data of a system is retained over time, reorganized but never generated or destroyed. Black holes, at first glance, seem to treat information in an innocent manner. They collect matter and all the information contained within it, and from the perspective of an outside observer, nothing ever enters a black hole. However, there is a slight complication. Black holes emit radiation, known as Hawking radiation, which is entirely thermal and random. This radiation is a result of the black hole's mass, spin, and charge, and nothing else affects its intensity or temperature. While information is neither created nor destroyed, the problem arises when the black hole eventually dissipates, causing the loss of information. Stephen Hawking discovered this phenomenon in the 1970s, and it raises the question of whether information can be preserved and recovered from a black hole. Black holes are mysterious and intriguing objects in the cosmos that raise many fascinating questions, one of which is the black hole information paradox. The cosmos values information and seems to dislike its creation or destruction, as information just exists and is neither generated nor destroyed. We can make predictions about the future behavior of a system based on the principles of physics, and the same physical rules that apply to the future also apply to the past if we have complete knowledge of the system. Therefore, information is retained over time because of this reversibility, and the system's basic data is just reorganized. However, black holes seem to treat information differently, as they collect matter and the data contained within them. From the perspective of an outside observer, nothing ever enters a black hole. But when black holes emit Hawking radiation, they lose energy and mass, ultimately leading to their disappearance along with the data they hold. This poses a paradox. What happens to the information if a black hole disappeared without emitting Hawking radiation? Many theorists have proposed possible solutions to this paradox, but they require rethinking nearly the entire body of existing physics. One solution is that the information is retained on the surface of the black hole, but it requires a major rewrite of physics to account for this unique scenario. Another solution is that the information does find its way into the Hawking radiation, but we don't yet have a means to observe and rebuild the lost information. Alternatively, the information may be left behind as a crunchy nugget when the black hole is about to evaporate completely, or it may travel through time and space and end up in a parallel universe. Let's talk about the Schrödinger's cat paradox, a thought experiment that has puzzled scientists for decades. In the 1960s, Hungarian-American physicist Eugene Wigner was both inspired and troubled by the paradox, which is based on the principles of quantum physics. Quantum physics deals with the world at a microscopic level and presents paradoxical ideas, such as the fact that a quantum system doesn't necessarily have definite qualities until it is observed. The paradox was famously created by physicist Erwin Schrödinger and involves a cat that is locked in a box with a vial of poison that will be released if a radioactive atom decays. Because radioactivity is a quantum process, the atom can be both decayed and not decayed at the same time, leaving the cat in a state of superposition between life and death. But what would it feel like to be both alive and dead at the same time? Wigner took this paradox one step further by considering what would happen if a human observer was also in the lab. He argued that it was absurd to suggest that the observer was also in a state of superposition until the moment the lab was opened. Wigner's friend thought experiments showed that if the observer is also being observed, things can get even stranger. Before the advent of quantum physics, physicists believed their theories to be deterministic, meaning that they produced precise predictions for the results of experiments. However, quantum theory is probabilistic by nature, and the prevailing theory was that consciousness somehow caused a superposition to collapse. This means that if Wigner's imaginary body took a measurement, they would be able to tell the result for sure, and Wigner would never see them in a state of superposition. Over the years, several interpretations of quantum mechanics have emerged that use less mystical mechanisms, such as decoherence, to explain how superpositions fail without involving awareness. Despite this, the Schrödinger's cat paradox continues to be a subject of fascination and debate among physicists. There are a number of interpretations that attempt to address Schrödinger's cat paradox in their own unique and fascinating ways. Some interpretations, like decoherence, aim to explain how superpositions collapse without invoking consciousness. Other interpretations take an even more extreme stance and suggest that there is no collapse at all. One such theory is the many worlds interpretation, which proposes that every time a quantum measurement is made, reality splits into parallel universes to accommodate all potential outcomes. According to this theory, Wigner's friend would be split into two copies, and with advanced technology, Wigner could actually measure their state of superposition while they were outside of the lab. For now, physicists will continue to debate which interpretation is correct, or whether a completely new theory is needed to resolve this paradox. Number 4. Young Sun Paradox. Researchers have been trying to solve the faint young sun paradox, which questions how Earth did not freeze billions of years ago when the sun was colder and only 70% as bright. This is because the heat felt on Earth during that time was far lower than what was expected. However, ancient rocks in ISU near Greenland's southwest coast show that liquid water and even life existed on Earth around 3.8 billion years ago, indicating that the climate of Earth had to be similar to the current temperature. This led scientists to believe that the atmosphere then had more greenhouse gases like carbon dioxide, which assist in warming the globe by absorbing solar heat. However, recent research has discovered that the quantities of greenhouse gases needed to explain the faint young sun paradox would have to be hundreds to thousands of times higher than they are now. Researchers examined relatively unaltered 3.8 billion-year-old rocks from a sewer and found no proof that greenhouse gas concentrations were high enough to account for the conundrum. They focused on mineral formations called serpentine, which preserve information about ancient seawater, including its hydrogen and oxygen isotope ratios that are dependent in parts on ocean size. Another theory suggests that there were fewer continents early in Earth's history, resulting in less land mass and fewer biologically produced particles like pollen and spores that could act as seeds around which clouds could form. This would result in less cloud cover, making the primarily ocean-covered Earth darker and able to absorb much more heat, keeping the Earth comfortable. Remember to subscribe to our channel to get the latest news from this world and beyond. Regarding other universe enigmas, there are many unsolved mysteries that scientists are trying to solve, such as the nature of dark matter and dark energy, the origins of cosmic rays and gamma rays, and the existence of parallel universes. As our understanding of the universe continues to evolve, we may eventually solve these mysteries and discover new ones. Click on the video links on your screens to access our other videos on a related subject to learn more about cosmic activities.